Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have triangle ABC. Triangle ABC is the right triangle. This is angle ABC. This is the right angle. Side AB equals to 6 units in its length. Side BC equals to 8 units in its length. Inside this right triangle ABC, we have this small circle and this big semicircle. And our mission is to find out the radius of this small circle. So, first of all, we'll implement the Pythagoras theorem in the right triangle, triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse in the right triangle ABC is AC, therefore the square of the hypotenuse is AC square. And AC square must be equal to AB square plus BC square. So I'll write it down. Here by PT is the relation for Pythagoras theorem. So AC square, that is the square of the hypotenuse, must be equal to AB square plus BC square. So again, in the right triangle ABC, according to the Pythagoras theorem, AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB is 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in conclusion, we found out that AC square equals to 36 plus 64. 36 plus 64 is 100. So in conclusion, we found out that AC square equals to 100. Here we take a root out of this equation and we find out that the length of the hypotenuse AC is equals to the square root of 100, that is 10. So the length of the hypotenuse AC is 10 units, so I write it down. AC equals to 10 units in its length. In the next step, we define the relevant points to this question with letters. We define the center of this small semicircle as point P. We define the center of this big semicircle, this point, as point Q. We will define the point of tendency of tangent AB with this small circle. This point is point N. We define the point of tendency of tangent AC with this small circle. This point is point K. Likewise, we define the point of tendency of tangent AC with this big semicircle, this point, as point H. And finally, we define the touching point of this small circle with this big semicircle. This point is point L. So here we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. If we focus on this common external point A, from this common external point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. So I write it down. According to rule 2, the length of tangent AB is equal to the length of tangent AH. But AB equals to 6 units in its length according to what is given us the question. So we can write here that AB equals to 6. And from this equation, 6 equals to AB equals to A edge. We will derive that A edge also equals to 6 units in its length. A edge equals to 6. So this times segment A edge equals to 6 units in its length. So I write it down here that A edge equals to 6 units in its length. What is the length of line segment edge C? The length of line segment edge C is AC minus A edge. Again, AC minus A edge equals to edge C. AC is 10, A edge is 6, so total edge C equals to 10 minus 6, that is 4. The length of line segment edge C is equals to 4 units in its length. In the next step, we will join points Q and H together by straight line. Point Q is the center of this big semicircle. Point H is the point on the semicircle itself. Therefore, QH is the radius of this big semicircle. We will define the radius of this big semicircle as B. Therefore, QH equals to B, it is the radius of the big semicircle. Here we can implement rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. We have here the radius QH that is equal to B, so the radius QH is drawn to point H, that is the point of tendency of tangent AC with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Okay, so by doing this construction, we created here triangle QHC. Triangle QHC is a right triangle, and this is angle C of triangle QHC. But angle C belongs also to the big right triangle, triangle ABC. So angle C is a common angle that belongs to both triangles. So we will define the size of this angle C as alpha. So in the right triangle HQC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we will focus on the big right triangle ABC. In the big right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees. Therefore, this third missing angle must be equal to 90 degrees minus alpha, according to the same rule, that the rule of the angles, according to the rule, that the sum of the angles in any triangle is equal to 180 degrees. So this missing angle must be equal to 90 degrees minus alpha. Okay. In the next step, we will prove that the big right triangle ABC is similar to the small right triangle QHC. So I write it down. We will prove that the big right triangle ABC is similar to this small right triangle QHC. So while the big right triangle ABC is similar to this small right triangle HC. First of all, those two angles they are both equal to 90 degrees, therefore they are equal to each other. Actually, this is angle ABC in the right triangle ABC, and it is equal to this angle. This is actually angle QHC in a small triangle HQC. So I'll repeat again. Angle ABC, the big right triangle ABC, equals to angle QHC in the small right triangle HQC. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles. So we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. If we relate to this angle alpha as it belongs to the big right triangle ABC, it will be defined as angle ACB, and angle alpha equals to itself. So if we relate to angle alpha as it belongs to the small right triangle HQC, it will be defined as angle HCQ. Again, this equation means that angle alpha equals to itself. We just call to angle alpha two different names. Angle alpha equals to itself is a common angle that belongs to all triangles. And finally, those two angles they are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually this is angle BAC in the big right triangle ABC, and it is equal to this angle, that is actually angle HQC in the small right triangle HCQ. Repeat again. We actually found out that angle BAC in the big right triangle ABC equals to angle HQC in the small right triangle HCQ. They are both equal to 90 degrees minus alpha, therefore they are equal to each other. So actually we found out that all the three angles in the big right triangle ABC are correspondingly equal to all the three angles in the small right triangle HCQ. Therefore those two right triangles are similar to each other according to angle similarity rule. So I write it down. I actually found out that the big right triangle ABC is similar, this is the sign of similar, to the small right triangle HQC according to angle similarity rule. And from the fact that the big triangle ABC is similar to the small right triangle HQC, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again. We will derive that side AB in the big right triangle ABC over side HQ Q in the small right triangle HCQ equals to side BC in the big right triangle ABC, or side HC in the small right triangle HCQ. AB is 6 over HQ. HQ is B, it is the radius of the big circle, that is equals to B according to our definition, and it is equals to BC. BC is 8 according to what's given the question, over HC. HC equals to 4 according to what we already found out. So we actually found out that 6 over B equals to 8 over 4. 8 over 4 is 2. So we found out that 6 over B equals to 2. Here we will multiply this equation by B, and we get that 6 equals to 2B. Here we will divide this equation by 2, and finally we get that the missing radius B equals to 6 over 2, that is 3. So we actually found out that the radius of this big semicircle B equals to 3 units in its length. Point Q is the center of this big semicircle. Point B is the point on the big semicircle itself. Therefore, QB is the radius of this big semicircle. And the radius of this big semicircle equals to 3. So write it down. QB equals to 3 units in its length. In the next step, we'll join points P and M. We will join points P and N together by a straight line. Point P is the center of this small circle. Point N is the point on the small circle itself. Therefore, Pn is the radius of this small circle. That is the radius that we are looking for in this question. We define the radius of this small circle as A. So Pn equals to A, it is the radius of the small circle. Here we can implement rule 1 because we have the radius Pn that is equal to A. The radius Pn is 1 to point N, that is the point of tendency of tangent AB with this small circle. And whenever we have a radius that is 1 to the point of tendency, then tangent AB will be perpendicular to the radius NP. If AB is perpendicular to NP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. Likewise, we join points P and K together by a straight line. PK is of course the radius of this small circle, that is equals to A according to our definition. Again, we have the radius PK that is equals to A. The radius PK is 1 to point K, that is the point of tendency of tangent AC with this small circle. And whenever we have a radius that is 1 to the point of tendency, then tangent AC will be perpendicular to the radius KP. If AC is perpendicular to KP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, I will present to you a new rule, and we will implement the new rule in our drawing. The new rule is rule 15. According to rule 15, if from an external point of a circle you draw two tangents to that circle, so here we have, this is the external point P. From this external point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing those two tangents PA and PB, we created here this angle, that is angle PAB. Okay. Then the angle that will be created between the two tangents, the angle that is created between tangent PA and tangent PB is angle PAB. This angle, and according to rule 15, its angle bisector must pass through the center of the circle. So according to rule 15, the angle bisector of angle APB, this angle, the angle bisector of this angle APB must pass through point O, that is the center of this circle. Again, the angle bisector of angle PAB must pass through point O, that is the center of this circle. So whenever you draw two tangents to a circle from a common extra point to the circle, you will create the angle that was created by the two tangents. The angle bisector of the angle that will be created by the two tangents PA and PB, the angle bisector of this angle must pass from point O, that is the center of this circle. So we can actually implement rule 15 in our drawing. Why? Because in our drawing, if you focus on this common extra point, point A, from this common extra point, point A, we have two tangents to this small circle, tangent AK and tangent AN. By drawing the two tangents AK and AN, we created this angle A. Again, this angle was created by drawing angle AK or tangent AK and tangent AN to this small circle. And according to rule 15, the angle bisector of this angle A must pass through point P, that is the center of this circle. Again, the angle bisector of this angle A must pass through point P, that is the center of this circle. So I'll draw the angle bisector of angle A, and it must pass from point P. So in conclusion, I found out that the angle bisector of this angle A must pass from point P. So I write it down. We actually found out that the angle bisector of angle A passes through point P, that is the center of this small circle. Okay? So if we define the size of angle A is 2 theta, then angle bisector PA bisects angle A to 2 halves. This is the first half is equals to theta, and this is the second half that will also equals to theta. We will continue to focus on this common extra point, point A. From this common extra point, point A, we have two tangents to this big semicircle, tangent AB and tangent AH. Actually, the two tangents that we created here, tangent AB and tangent AH, created this angle, angle A. It is the same angle, angle A. Now we can implement rule 15 because we have tangent AB and tangent AH, and the angle that was created between those two tangents is angle A. The same angle, angle A. According to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, according to rule A, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. So I draw the angle bisector of angle A. It must pass from point Q. It must start, of course, from point A, and it must pass from point Q. It is the same angle bisector of angle A. So in conclusion, actually found out that the angle bisector of this, the same angle A, must pass also from point Q, that is the center of this big semicircle. So I'll write it down. We actually found out that the angle bisector of angle A passes also through point Q. In conclusion, actually found out that the angle bisector of this angle A passes from point P and from point Q. In addition, the angle bisector of this angle A, of course, it passes through point A. So I write it down. The angle bisector of this angle A passes, of course, through point A. So I write it down. The angle bisector of angle A passes also through point A. In conclusion, actually found out that the angle bisector of this angle A passes through points A, P, and Q. So I write it down. Actually found out that the angle bisector of angle A passes through points A, P, and Q. A, P, and Q. Okay, again, the angle bisector of this angle A passes through points A, P, and Q. But the angle bisector of angle A, it is a straight line. Therefore, you can write down that points A, P, and Q, they are located on the same straight line. So I write it down. Actually found out that points A, P, and Q, they are all located on the same straight line, and the straight line is of course the angle bisector of angle A. So I write it down. The straight line is the angle bisector of angle A, that it is a straight line. Okay, or we can also say that line segment APQ is one straight line. Again, line segment APQ is one straight line. So write it down. Carefully found out that line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is a straight line. Therefore, AQ is a straight line. And if AQ is a straight line, it means that shape ABQ, this shape ABQ is a right triangle. Therefore, shape ABQ is a right triangle. And this is angle theta that is belongs to the right triangle ABQ, but angle theta also belongs to the right triangle ANP. Therefore, angle theta is a common angle that belongs to both triangles. So, in the right triangle ABQ, this angle equals to theta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, we focus on this small right triangle A and P. In the small right triangle A and P, this angle equals to theta, this angle equals to 90 degrees. Therefore, this first missing angle must be equal to 90 degrees minus theta, according to the same rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will prove that the big right triangle ABQ is similar to this small right triangle ANP. Repeat again. We'll prove that the big right triangle ABQ is similar to the small right triangle ANP. So why the big right triangle ABQ is similar to this small right triangle ANP? First of all, those two angles, they are both equal to 90 degrees, therefore they are equal to each other. So I write it down. This is angle ABQ in the right triangle ABQ. And it is equal to this angle, that is actually angle ANP in the small right triangle APN. Repeat again. Therefore, found out that angle ABQ in the right big triangle ABQ equals to angle ANP in the small right triangle APN. They are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, that is a common angle that belongs to both triangles. Okay? So okay, I know that angle theta equals to itself as a common angle that belongs to both triangles. If we relate to this angle theta as it belongs to the big right triangle ABQ, it will be defined as angle BAQ. And angle theta equals to itself. So if we relate to angle theta, as it belongs to the small right triangle ANP, it will be defined as angle NAP. Repeat again. This equation means that angle theta equals to itself. We just called to angle theta two different names. Angle theta equals to itself is a common angle that belongs to both triangles. And finally, those two angles, they are both equal to 90 degrees from each other, therefore they are equal to each other. This is actually angle AQB. In the right big triangle ABQ, and it is equal to this angle, that is actually angle APN, in the right small triangle ANP. Repeat again, I actually found out that angle AQB in the big right triangle ABQ equals to angle APN in the small right triangle ANP. They are both equal to 90 degrees from each other, therefore they are equal to each other. So we actually found out that all the triangles in the big right triangle ABQ are correspondingly equal to all the triangles in this small right triangle ANP. Therefore, those two right triangles are similar to each other according to angle similarity rule. So I write it down. The big right triangle ABQ is similar, this is the sign of similar, to the small right triangle ANP according to angle similarity rule. And from the fact that the big right triangle ABQ is similar to this small right triangle ANP, we will derive that the following relationship exists between their sides. We will derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again, we derive that side AB in the big right triangle ABQ over side AN in the small right triangle ANP equals to side BQ in the big right triangle ABQ over side ANP in the small right triangle ANP. AB is 6 over AN. AN is the missing side, so we will leave it as it is. And it is equals to BQ. BQ is the radius of this big semicircle that is equals to 3 units in its length over NP. NP equals to A. It is the radius of this small circle that is the radius that we are looking for in this question. So in conclusion, we can find out that 6 over AN equals to 3 over A. Here we first multiply this equation. And we will get that 6A equals to 3 times AN Here we divide this equation by 3 and we get that the missing side AN equals to 6A over 3. 6A over 3 is 2A. In conclusion, we should find out that this missing side AN is equals to 2A units in its length. So I write it down. The missing side AN equals to 2A units in its length. So we know that side AB equals to 6 units in its length, side AN equals to 2A units in its length. Therefore, the missing line segment NB must be equal to AB minus AN. AB is 6, AN is 2A, so in total NB equals to 6 minus 2A. So I write it down. The length of this line segment NB is equals to 6 minus 2A units. In the next step, we'll draw perpendicular from the center of this small circle, that is point P, on BQ. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We will define the touching point of the perpendicular from point B and BQ. This point is point Z. By doing this construction, we can deduce quadrilateral NP PZ. In quadrilateral NP BZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any triangle is equal to 360 degrees. Therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrilateral NPBA, NPBZ, we have 4 right angles. And according to rule 5, any quadrilateral that has 4 right angles must be at least a rectangle, if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. So I write it down. This quadrilateral NPBZ is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ, but NPZ over BZ must be also equal to A. Likewise, according to the same rule, in the same rectangle NPBZ, side NB must be equal to the opposite side PZ, but NB is 6 minus 2A, therefore the opposite side PZ must be also equal to 6 minus 2A. So I write it down. PZ equals to 6 minus 2A units in its length. What is the length of this PC97 ZQ? From the drawing it is very easy to see that ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. So ZQ equals to BQ, that is 3, minus BZ, that is A. So in total, ZQ equals to 3 minus A. So I write it down. What is the length of line 7PQ? Actually, we'll find out the length of line 7PQ by implementing rule 10 in our drawing. I repeat quickly on rule 10. According to rule 10, if two circles have an external notch between them, then the straight line that connects their centers together must pass through their touching points. So in the drawing we have two circles. Those two circles touch each other externally at point P. That is to say, they have an external notch between them at point P, and therefore the center of this small circle is there at point M. The center of this big circle is there at point O. And the straight line that connects their centers together is of course the straight line MO. So this straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. or MPO is one straight line. Again, MPO is one straight line according to this rule, rule 10. Rule 10. So actually we can implement rule 10 in our drawing. Why? Because in our drawing we have an external notch between this small circle and this big semicircle. That is to say they are touching each other externally at point L. And therefore we can implement a rule 10. The center of this big small circle is there at point P. The center of this big semicircle is there at point Q. And the straight line that connects the centers together is of course the straight line PQ. This straight line PQ must pass through point L, that is their touching point. I repeat again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line according to rule 10. And because of the fact that PLQ is one straight line, it means that PQ is also a straight line. And PQ will be equal to PL plus LQ. Again, PQ equals to PL plus LQ. So I write it down. PQ equals to PL plus LQ. Actually, it is not trivial at all to say that PQ equals to PL plus LQ, only because of the fact that PLQ is one straight line. We can say that PQ equals to PL plus LQ. Okay, so PQ equals to PL. PL is the radius of this small circle. This equals to A. A is the radius that we are looking for in this question, plus LQ. LQ is the radius of this big semicircle that is equal to 3 units in itself. So LQ equals to 3. So in total, we shall find out that PQ equals to A plus 3. Okay, therefore PQ is A plus 3 units. In the next step, I'll copy this green right angle PZQ in a new page, and we'll implement the Pythagoras theorem on this right green triangle PZQ. Side PZ equals to 6 minus 2A. Side ZQ equals to 3 minus A. And the hypotenuse PQ equals to 3 plus A. Here by PT is the relation for Pythagoras theorem. Actually, this is the right green triangle PZQ that I copied from the original drawing. According to the Pythagoras theorem, in this right triangle PZQ, PQ squared, that is the square of the hypotenuse, must be equal to PZ squared plus ZQ squared. Again, PQ squared equals to PZ squared plus ZQ squared. So I write it down. So PQ squared, that is the square of the hypotenuse, equals to pz square plus zq square. pq is 3 plus a, therefore pq square is 3 plus a square, and it is equals to pz square. Pz is 6 minus 2a, therefore pz square is 6 minus 2a square plus zq square. zq is 3 minus a, therefore zq square is 3 minus a square. So in conclusion, we shall find out that 3 plus a square equals to 6 minus 2a square plus 3 minus a square. Here we'll open the brackets on both sides of this equation, and we get that 3 plus a square equals to 3 squared, that is 9, plus a square plus 2 times 3 times a, that is 6a. And it is equals to 6 minus 2a squared. 6 minus 2a squared equals to 6 squared, that is 36, plus 2a squared, that is 4a squared, minus 2 times 6, that is minus 12, times 2a. Minus 12 times 2a is 20, minus 24a. Plus 3 minus a squared. 3 minus a squared equals to 3 squared, that is 9, plus a squared minus 2 times 3 times a, that is minus 6a. So here we have 9 on both sides of the equation, so 9 will get cancelled. We have also a squared on both sides of the equation, so a squared also will get cancelled. So what is left from this expression of the cancelled those two expressions? In this side of the equation we left only with 6a. In the other side of the equation we have 36 plus 4a squared minus 24a. Here we subtract 6a from this equation. After we subtract the 6a, in this side of the equation we left with nothing, that is to say 0. On the other side of the equation we have 36 plus 4a squared, and we have minus 24a minus 6a is minus 30a. Here we have minus 24a minus 6a is minus 30a. So here we have minus 30a and not minus 24a. Again, minus 24a minus 6a is minus 30a. Now minus 30a minus 6a is minus 36a. So we actually found out that 36 plus 4a squared minus 36a equals to 0. Here we divide this equation by 4, and we get that 4a squared over 4 is a squared, minus 36a over 4 is minus 9a, and 36 over 4 is 9. 0 over 4 is 0. We found out that a squared minus 9a plus 9 equals to 0. So this is a quadratic equation. Okay. And the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times a times c over 2a. Now a specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0. The variable that we are looking for in this specific quadratic equation is a, so x equals to a. The coefficient a equals to 1. The coefficient b equals to minus 9, and the coefficient c equals to 9. The only thing that is left to do is to put the data inside the data for our specific quadratic equation in this general formula for x, and we find out the value or the values of a, because x equals to a. We do it now, and we get that x equals to a, so we have x equals to a, so a equals to minus b. B equals to minus 9, therefore minus b is minus 9, that is plus 9, plus minus square root of b squared. B is minus 9, therefore b squared is minus 9 squared, that is 81. Minus 4 times a is 1, so minus 4 times 1 is minus 4, times c is minus 9, so c is 9, here c is 9, so minus 4 times 9 is minus 36, so in total inside the root we have 81 minus 36 divided by 2a. A is 1, so 2a is 2 times 1, that is 2. So a equals to 9 plus minus square root 81 minus 36 is 45. So inside the root we left only with 45 over 2. So here we have two solutions that are possible for a. The first solution for a, that is the radius of this a, that is the radius of this small circle, that is the radius that we are looking for in this question. So the first solution for the radius of the small circle a is that a equals to 9 plus square root of 45 over 2. This expression 9 plus square root of 45 over 2 is definitely greater than 3. So according to the first solution for a, we actually found out that the radius a of this small circle is greater than 3 units. But it is impossible actually that the radius a of this small circle is greater than 3 units, because of the fact that we already found out that the radius of this big semicircle, the radius p equals to 3 units in its length. The big semicircle is definitely greater than the small circle, and therefore the radius of the big semicircle must be greater than the radius of this small circle. That is to say, the radius of this small circle a must be less than 3 units. But according to the first solution, the radius of the small circle a is greater than 3 units. So this solution is incorrect solution. We cancel the solution, and we left only the second solution that is possible for a. The second solution for a is that a equals to 9 minus square root of 45 over 2. So a equals to 9 minus 45 is 9 times 5, so we substitute 45 by 9 times 5 divided by 2. So a equals to 9 minus the square root of 9 is 3. So inside the root we left only with 5 divided by 2. So actually found out that the radius a of this small circle, that is the radius that we are looking for, equals to either 9 minus 3 times square root of 5 over 2 units in its length, or in terms of numbers, it is equals to 1.146 units in its length. Okay, that is less than 3 units. That is the radius of the big semicircle. So actually, uh, the radius of the big semicircle, it is about 3 times longer than the radius of this small circle. Y equals the radius of the small circle, A equals to 1.146 units. Okay, so we finished with the question. In the next step, I'll summarize the lecture. In this lecture, we found out the radius of this small circle. In the domain, we have a right angle ABC. We know that side AB equals to 6 units in its length, side BC equals to 8 units in its length. Inside this big right angle ABC, we have this small circle and we have this big semicircle. And our mission is to find out the radius of this small circle. So in the first step, we implemented the Pythagoras theorem in the right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, in the right triangle ABC, AC square equals to AB square plus BC square. Repeat again. In the right triangle ABC, the Pythagoras theorem means that AC square equals to AB square plus BC square. AC is the missing side, so we leave it as it is. AC square equals to AB square. AB 6, therefore AB square is 6 squared, that is 36, plus BC square. BC is 8, therefore BC square is 8 squared, that is 64. So in total, AC square equals to 36 plus 64, that is 100. So AC square equals to 100. We took a root out of this equation and finally found out that the missing hypotenuse AC is equal to the square root of 100, that is 10. So the length of the hypotenuse AC is 10 units in its length. In the next step, we define the relevant points to this question with letters. We define the center of this small circle, this point is point P. We define the center of this big semicircle, this point is point Q. We define the point of tendency of tangent AB with this small circle, this point is point N. We define the point of tendency of tangent AC with this small circle, this point is point K. We define the point of tendency of tangent AC with this big semicircle, this point is point H. And finally, we define the touching point between this small circle and this big semicircle, this point is point L. So here we can implement rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. So if you focus on this common external point, point A, from this common external point, point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And according to rule 2, they are equal to each other. That is to say, AB equals to AH. So repeat again. According to rule 2, AB equals to AH. But it is given us the question that AB equals to 6, so we can write here that AB equals to 6, and from this equation 6 equals to AB equals to AH, we will derive that AH equals to 6. So here, line segment AH equals to 6 units in its length. What is the length of line segment HC? It is very easy to see from the drawing that HC equals to AC minus AH. Again, AC minus AH equals to HC. So HC equals to AC, that is 10, minus HC, that is 6. So in total, HC equals to 10 minus 6, that is 4. In the next step, we join points Q and H together by straight line. Point Q is the center of this big semicircle. Point H is the point of the big semicircle itself. Therefore, QH is the radius of this big semicircle. We define the radius of this big semicircle as B. So QH equals to B. Here we can implement rule 1. According to rule 1, a tangent to the circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius QH that is equal to B. The the radius QH is drawn to point H, that is the point of tendency of tangent AC with this small circle, with this big semicircle. And whenever you have a radius that is drawn to the point of tendency, then tangent AC will be perpendicular to the radius HQ. If AC is perpendicular to HQ, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule 1. By doing this construction, the right triangle QHC. This is angle C that belongs to the right triangle QHC, but angle C also belongs to the big right triangle ABC, so angle C is the common angle that belongs to both triangles. To the right small triangle QHC and to the right big triangle ABC. So we define the size of this angle C as alpha. So in the right small triangle HQC, this angle equals to alpha, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus alpha. Why? Because 90 degrees minus alpha plus alpha is 90 degrees, and 90 degrees plus 90 degrees, it is equal to 180 degrees, that is the sum of the angles in any triangle. Likewise, if you focus on the right triangle ABC, this angle equals to alpha, this angle equals to 90 degrees, therefore this missing angle must be equal to 90 degrees minus alpha. In the next step, we proved that the right big triangle ABC is similar to this right small triangle HQC. So why those two right triangles are similar to each other? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle alpha, that is a common angle, it belongs to both triangles, so we can write down that angle alpha equals to itself as a common angle that belongs to both triangles. And finally, those two angles are both equal to 90 degrees minus alpha, therefore they are equal to each other. So we should prove that all the three angles in the right big triangle ABC are correspondingly equal to all the three angles in this small right triangle QHC. Therefore we should prove that those two right triangles are similar to each other according to angle similarity rule. So I repeat again, we should prove that the right big triangle ABC is similar, this is the sign of similar, to the right small triangle HQC according to angle similarity rule. And from the fact that the right big triangle ABC is similar to the right small triangle HQC, we will derive that the following relationship exists between their sides. We will derive that side AB in the right triangle ABC over side HQ in the small right triangle HQC equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. Repeat again. We will derive that side AB in the big right triangle ABC over side HQ in the small right triangle HCQ equals to side BC in the big right triangle ABC over side HC in the small right triangle HCQ. AB is 6, HQ is B, this is the radius of the big circle, the big semicircle, that is equals to B, BC is 8, and HC is 4. So we actually found out that 6 over B equals to 8 over 4. 8 over 4 is 2, so in total we found out that 6 over B equals to 2. We multiplied this equation by B and finally found out that 6 equals to 2B. We divided this equation by 2 and finally found out that the missing radius B of the big semicircle is equal to 3 units in its length. So this is HQ, that is the radius of this big semicircle, that equals to 3 units in its length. Point Q is the center of the big semicircle, point B is the point of the big semicircle itself, therefore BQ is also the radius of this big semicircle that is equal to 3 units in its length. In the next step, I presented to you a new rule and implemented the new rule in our drawing. The new rule is rule 15. Repeat quickly on rule 15. According to rule 15, if from an external point of a circle you draw two tangents to the circle, so here we have, this is the external point P. From this external point P, we draw two tangents to this circle, tangent PA and tangent PB. By drawing the two tangents PA and PB, we created here angle APB. Then the angle that will be created between the two tangents, that is to say, the angle that will be created between the tangent PA and tangent PB is of course this angle. And according to this rule 15, its angle bisector must pass through the center of the circle. So the angle bisector of this angle APB, this angle, must pass through point O, that is the center of this circle. So whenever you draw two tangents from a common standpoint towards a circle, PA and PB, we create angle APB. That is the angle that's created between the two tangents PA and PB. According to rule 15, the angle bisector of this angle APB must pass through point O, that is the center of this circle. So we can implement rule 15 in our drawing. Why? Because in our drawing, if we focus on this common external point A, from this common external point A, we have two tangents to this small circle, tangent AN and tangent AK. Those two tangent AN and AK, by drawing the two tangent AN and AK, we created here angle A. Again, this angle A was created by drawing tangent AN and tangent AK to this small circle. So according to rule 15, the angle bisector of angle A must pass through point P, that is the center of this small circle. So PA is the angle bisector of angle A, and PA of course passes through point P, that is the center of this small circle. So from here you can write down that the angle bisector of angle A passes through point P. If we continue to focus on this common external point A, from this common external point A, we have two tangents to this big semicircle, tangent AB and tangent AH. And the angle bisector that was created by tangent AB and tangent AH is the same angle, angle A. So according to rule 15, the angle that was created between tangent AB and tangent AH is angle A. And according to rule 15, the angle bisector of this angle A must pass through point Q, that is the center of this big semicircle. Again, the angle bisector of angle A must pass through point Q, that is the center of this big semicircle. So you can see here that the angle bisector QA passes through point Q, that is the center of this big semicircle. So if we define the size of angle A as 2 theta, then the angle bisector QA bisects angle A into 2 halves. Each half must be also equal to theta, of course. Likewise, the angle bisector PA of the same angle A bisects angle A into 2 halves. Each half equals to theta. So we can write down actually that the angle bisector of angle A passes through point T. Okay, the angle bisector of angle A passes through point Q. And the angle bisector of angle A, of course, passes through point A. Here, the angle bisector of angle A passes also through point A. In conclusion, can write down that the angle bisector of this angle, angle A, passes through points A, P, and Q. Repeat again. Actually found out that the angle bisector of angle A passes through points A, P, and Q. Or in other words, we can say that points P, A, P, and Q, they are all located on the same straight line. Why? Because we know that the angle bisector of any angle is a straight line. The angle bisector of angle A is a straight line. And the 3 points A, P, and Q are located on the angle bisector A, that is the straight line. So all the 3 points A, P, and Q are located on the same straight line. And the straight line is the angle bisector of A. And in other words, we can say that the line segment APQ is one straight line because of the fact that the 3 points A, P, and Q they are all located on the same straight line. You can say that line segment APQ is one straight line. And line segment APQ is one straight line. If line segment APQ is one straight line, it means that AQ is also a straight line. And if AQ is a straight line, it means that shape ABQ is a right triangle. Again, shape ABQ is right angle. And again, we should found out that shape ABQ is right angle. So in the right triangle ABQ, this is angle theta, but angle theta belongs also to the right small triangle ANP. So in the right triangle ABQ, this is angle theta, this angle equals to 90 degrees, and therefore this first missing angle must be equal to 90 degrees minus theta. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees is equals to 180 degrees. That is the sum of the angles in any triangle. Likewise, in the right triangle ANP, this angle equals to theta, this angle equals to 90 degrees. Therefore, this missing third angle must be equal to 90 degrees minus theta. According to the third rule, that the sum of the angles in any triangle is equal to 180 degrees. The next step, we should prove that the right big triangle ABQ is similar to the right small triangle ANP. So why the right big triangle ABQ is similar to the small right triangle ANP? First of all, those two angles are both equal to 90 degrees, therefore they are equal to each other. In addition, this is angle theta, this is a common angle that belongs to both angles, so we can write down that angle theta equals to itself as a common angle that belongs to both angles, and finally, those two angles are both equal to 90 degrees minus theta, therefore they are equal to each other. So I should prove that all the figures of the right triangle ABQ are correspondingly equal to all the figures of the right small triangle ANP, therefore those two right angles are similar to each other according to angle similarity rule. So I repeat again, I should have found out that the right triangle ABQ is similar to the right triangle ANP according to angle similarity rule. And from the fact that the right triangle ABQ is similar to the small right triangle ANP, we will derive that the following relationship exists between their sides. We will derive the side AB, the right big triangle ABQ, over side AN in the small right triangle ANP, equals to side BQ on the big right triangle ABQ over side NP in the small right triangle ANP. Repeat again, we will derive that side AB in the right big triangle ABQ over side AN in the right small triangle ANP equals to side BQ in the right big triangle ABQ over side NP in the right small triangle ANP. AB is 6, AN is the missing side, so we leave it as it is. BQ is 3, it is the radius of the big semicircle, that is equals to 3 units in its length. And finally, NP is A. A is the radius that we are looking for in this question. So in conclusion, I actually found out that 6 over AN equals to 3 over A. We cross multiplied this equation and finally found out that 6A equals to 3 times AN. Here we divided this equation by 3 and finally found out that the missing side AN equals to 6A over 3. 6A over 3 is 2A. So we actually found out that this missing side AN equals to 2A units in its length. AB equals to 6. AN equals to 2A. Therefore, the missing line segment NB must be equal to AB minus AN. AB is 6. AN is 2A. So in total, NB must be equal to 6 minus 2A. NB equals to 6 minus 2A. In the next step, we did the construction, that is to say, from point P, that is the center of this small circle, we go perpendicular on BQ. Again, from point P, we go perpendicular on BQ. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BQ. This point is point Z. By doing this construction, we get the quadrilateral NPBZ. In quadrilateral NPBZ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees according to the rule that the sum of the angles in any triangle is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So in the right triangle NPBZ, we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be it is a rectangle if not a square. So we relate to quadrilateral NPBZ as a rectangle because it has 4 right angles. It is a rectangle. Okay, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NPBZ, side NP must be equal to the opposite side BZ. But NPZ, therefore BZ must be also equal to A. Likewise, according to the sum rule in the same rectangle, side NB must be equal to the opposite side PZ. But NB is 6 minus 2A, therefore PZ must be also equal to 6 minus 2A. What is the length of line segment ZQ. From the drawing, it is very easy to see that ZQ equals to BQ minus BZ. Again, ZQ equals to BQ minus BZ. ZQ equals to BQ, that is 3, minus BZ, that is A. So in total, ZQ equals to 3 minus A. What is the length of PQ? The length of line segment PQ, actually found out what the length of line segment PQ by implementing all 10 in our drawing. Why? Because we can implement all 10 in our drawing. Why? Because in our drawing we have an external edge between this small circle and this big semicircle. That is to say, they are touching each other externally, this point L. And whenever we have an external edge between two circles, you can implement all 10. So I'm going to go on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their centers together must pass through their touching points. So in the drawing we have two circles. Those two circles touch each other externally at this point P. We have an external between them at point P. The center of this small circle is at point M. The center of this big circle is at point O. And the straight line that connects their centers together is of course the straight line MO. And according to this rule 10, the straight line MO must pass through point P, that is their touching point. Again, the straight line MO must pass through point P, that is their touching point. Or MPO is one straight line. Again, MPO is one straight line. We can actually implement rule 10 in our drawing. Why? Because in our drawing, we have an external edge between the small circle and the big semicircle, that is to say they are touching each other externally at point A, at point L. The center of this small circle is at point P. The center of this big semicircle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass through point L, that is their touching point. Again, the straight line PQ must pass through point L, that is their touching point. Or PLQ is one straight line. Again, PLQ is one straight line. If PLQ is one straight line, it means that PQ is also a straight line. So what is the length of PQ? PQ equals to PL plus LQ. Again, PQ equals to PL plus LQ. So PQ equals to PL. PL equals to A. That is the radius that we are looking for in this question. Plus LQ. LQ equals to 3. It is the radius of this big semicircle. That is equals to 3. So in conclusion, we found out that PQ equals to 3 plus A. In the next step, I copied this right rectangle PZQ in a new page and implemented the Pythagoras theorem on this right rectangle PZQ. This is the right rectangle PZQ that I covered from the random domain. PZ equals to 6 minus 2A, ZQ equals to 3 minus A, and the opponent PQ equals to 3 plus A. According to the Pythagoras theorem, in this right triangle PZQ, PQ square equals to PZ square plus ZQ square. Again, PQ square equals to PZ square plus ZQ square. PQ is 3 plus A, therefore PQ square is 3 plus A square, and it is equals to PZ square. PZ equals to 6 minus 2A, therefore PZ square equals to 6 minus 2A square, plus ZQ square. ZQ is 3 minus A, therefore ZQ square is 3 minus A square. We open the brackets on both sides of this equation. 3 plus A square equals to 3 square, that is 9, plus A square, plus 2 times 3 times A, that is 6A, and it is equals to 2. On the other side of the equation, we have 6 minus 2A squared. 6 minus 2A squared equals to 6 squared, that is 36, plus 2A squared, that is 4A squared, minus 2 times 6, that is minus 12, minus 2A. Minus 12 minus 2A is minus 24A, plus 3 minus A squared. 3 minus A squared equals to 3 squared, that is 9, plus A squared, minus 2 times 3 minus A is minus 6A. So here we have 9 on both sides of the equation, so 9 will get cancelled, and we have also A squared on both sides of the equation, so A squared also will get cancelled. So what is left from this equation after cancelling those two expressions? In this side of the equation we left only with 6A, and the other side of the equation we have 36 plus 4A squared, and here we have minus 24A minus 6A is minus 30A. So in conclusion, we should have found out that 6A equals to 36 plus 4A squared minus 30A. Here we subtracted 6A from the equation and finally found out that here, after subtracting 6A, we left with nothing, that is to say 0. On the other side of the equation, we have 36 plus 4A squared, and minus 38 minus 6A is minus 36A. So in conclusion, actually found out that 0 equals to 36 plus 4A squared minus 36A. Here we divided this equation by 4, And finally found out that 4a squared over 4 is a squared. Minus 36a over 4 is minus 9a, and minus 36 over 4 is 9. So in conclusion, we found out that a squared minus 9a plus 9 equals to 0. So this is a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. In this general formula, a, b, and c are the coefficients of this quadratic equation, and x is the variable that we are looking for. And we find out the value of x according to the following formula: x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. Another specific quadratic equation, that is to say a squared minus 9a plus 9 equals to 0, the variable that we are looking for is a. So x equals to a, the coefficient a equals to 1, the coefficient b equals to minus 9, and the coefficient c equals to 9. The only thing that is left to do is to put the data for our specific quadratic equation inside this general formula for x, and we find out the values of a, because x equals to a. And a is the radius of this small circle, that is the radius that we are looking for in this question. So we did it, and we found out again x equals to a, so a equals to minus b. b is minus 9, therefore b is minus 9, that is plus 9, plus minus square root of b squared. b is minus 9, therefore b squared is minus 9 squared, that is 81, minus 4 times a is 1, so minus 4 times 1 is minus 4, times c is 9, so minus 4 times 9 is minus 36. So inside the root we have 81 minus 36 divided by 2. So a equals to 9 plus minus square root 81 minus 36 is 45 divided by 2. So here we have two solutions that are possible for a. The first solution for a is that a equals to 9 plus square root of 45 over 2. But 9 plus square root of 45 over 2 is greater than 3. So we found out that according to the first solution for a, the radius a of this small circle is greater than 3 units. But it is impossible that the radius a of this small circle is greater than 3 units, because of the fact that the radius of this big semicircle equals to 3 units. And the big semicircle is definitely bigger than this small circle, and therefore the radius of this big semicircle must be greater than the radius of this small circle. So if the radius of this big semicircle is 3, it means that the radius of this small circle must be less than 3. So the answer, the solution that the radius of the small circle is greater than 3 is the incorrect solution. We cancel the solution, and we left only with the second solution that is left for a, that the radius a of the small circle equals to 9 1 square root of 45 over 2. 45 is 9 times 5, so we substitute 45 by 9 times 5. We actually found out that a equals to 9 1 square root of 9 times 5 over 2. The square root of 9 is 3, so inside the root we left only with 5. In conclusion, we actually found out that the radius a of the small circle equals to 9 minus 3 times square root of 5 over 2 units. In terms of numbers, the radius a of this small circle equals to 1.146 units in its length. Repeat again, the radius a of this small circle equals to either 9 minus 3 times square root of 5 over 2 units in its length. In terms of numbers, the radius a of this small circle equals to 1.146 units in its length. This is smaller than the radius of this big semicircle, that is 3. Okay, thank you very much.